All right. Good afternoon, everybody. Thank you for coming. So let me begin with a very brief summary of what we covered in the previous lecture. I think it was primarily, we were thinking about PCA. And I started with this picture of, we have some data sets, and we're trying to find a particular direction, U1, such that the variance is maximized. And the way we did it was by saying I'm going to have a random vector that belongs to RD. We assume that the expected value of x was equal to 0. We assume that the covariance of x was a certain given matrix. And we define the principal components, y sub I, as a linear component of x. Okay? And we define them that the y sub i's need to be uncorrelated, linear components of maximum variance. That was the definition. And so what we require was that the variance of y1 be bigger than or equal to the variance of y2, and so on and so forth. Okay? That was the definition of principal components. And we proved that u sub I is equal to the I largest eigenvector of sigma x. Okay? And we also proved that the variance of y is equal to the I largest eigenvalue of sigma x. So in this picture, if this is the origin, this is what lambda 1 is going to be. Okay? And this is what u1 is going to be. And we also proved that ui is perpendicular to uj for I different from j. In other words, these principal directions, if you wish, are orthogonal to each other. And so u2 is going to be in that direction. And we proved that the principal components being uncorrelated implies that these vectors are orthogonal. Okay? That's a little bit the summary of the previous lecture. Okay? So what I'm going to do today is three things. First, I'm going to briefly relax the assumption that it's zero mean. And I say briefly because most of it is really in the homework. So I'm just going to modify a little bit the definition. Second, this isn't really something that you can apply in practice. And that's why I didn't describe an algorithm yet. The reason being the following. The starting point is that I know the mean and I know the covariance of a random variable. So everything that I've written here doesn't really operate on data, but rather it operates on the covariance of x. So in other words, it's like there is some probability model, and I know the covariance of the population, and based on that, I can find the principal components of the population. But effectively, this picture that I draw here is not quite correct, because it's actually, I don't have a data point insofar. Everything, really, is just done from that covariance matrix, X. So the next step is really going to be, how do I do it really from data? And so that's going to be the second part of the lecture today. And the last part is going to be that one interpretation, and everything I've said here is statistical, so finding directions with large variance. But there is a pure geometric interpretation of PCA as well in terms of finding a subspace that best fit the data. And I'm going to show that they are equivalent and how they are related. And this last interpretation is the one that is really going to lead to an actual algorithm that you can implement. And so the second homework is to implement PCA and apply it to a data set. Okay. So let me begin then briefly with the first extension, which is what if the data is not zero mean? So assume now that the expected value of x is equal to mu, right? And as before, the covariance of x is sigma x. Okay. So this mu is a vector that belongs to Rd, and as before, the covariance is a matrix that belongs to D times D. So in that particular case, what changes in terms of defining the principal components? The main change simply is that now y sub I is equal to u sub I transpose x, but I now need an extra bias term. Okay. So instead of being a linear component, is what we call an affine component. So if you might remember that from linear algebra, it's like I can have subspaces that go through the origin, or maybe the origin is someone else. And so subspaces or vectors that are not passing through the origin, then you have an affine relation. It's like a line. Does the line go through the origin or not? It's the same idea. So that's why we add this extra term here. Okay? But other than that, everything is the same. And so in fact, because this is in the homework, I'm not going to do it for you. You have to do it in the homework. But what changes by adding this extra mu? The main thing that changes is the following. Well, now, in order to estimate the principal components, I need to estimate not only the vector u, which I already knew it was the eigenvectors of sigma, but I also need to estimate this shift, a sub I. Okay? So in the homework 18, I think, you have to prove, if I'm not mistaken, that a sub I can be estimated as minus u sub I transpose the expect mu. You are going to prove that in the homework. Okay? Does that help? Is that really a solution? Not entirely, because supposedly, right, the starting point is that I know the mean and I know the covariance, so I know mu, but I don't know u sub I yet. Okay. But the main thing is that the rest is the same. So u sub I is still going to be the I eigenvector of sigma x. And lambda I is still going to be, or the variance of y sub I, still going to be the I eigenvalue of sigma. Okay? So the bottom line is that not much changes, okay? That still the main directions have to do exclusively with the covariance of the covariance matrix. And the extra thing is that I have this extra affine term that I can obtain by simply doing the dot product between that ith direction that I know and the mean of the data that is given to me. And so in particular, if the mean is 0, which was the previous case that I discussed in class, then all of the a sub i's are 0. And so they become redundant. Okay? So it's a very minor modification, and in the homework you have to prove this. Okay? So that was my first point. So let me now move to my second point, and that's the more important, and that is, well, in reality, I'm given data, and I don't know mu, and I don't know sigma x. So what do I do? Okay. So assume now we are given many data points, so x1, x2, xn. Right? So now I'm really given data points. They're all points in Rd. Okay? Okay. So now, you probably have seen in many lectures and many other courses what a Gaussian distribution is. Have you? you've seen also how do you estimate the parameters of a Gaussian, right? So, in particular, let's suppose, for the sake of simplicity, that X is distributed with some normal distribution with mean mu and, let me put it here, mu x if you want, and sigma x if you want. Okay? So, there is a procedure for estimating the parameters of a Gaussian that is called maximum likelihood. Who has never heard of maximum likelihood? Everybody knows. Okay, good. So, can you tell me then, if I give you many examples and samples from a Gaussian distribution, how do I estimate the mean? What is the maximum likelihood estimate for the mean of a Gaussian? The sum of the total number? Any correction to that?
Over the number.
Over the number. Okay. So then, the maximum likelihood estimator for mu is equal to what I'm going to call mu n hat here. It's 1 over n sum of the xj. Right? So the maximum likelihood estimator is the average of the data point. Okay? What about now the maximum likelihood estimator for sigma x? What is the optimal way to estimate the covariance? Anyone knows?
X 1 over n squared times x minus mu squared.
Okay, so 1 over n squared times
The sum from j equals 1 to n of xj minus mu squared.
xj minus mu squared. Okay. Anyone has an objection to that? Yes?
X is a vector, so we
X-
need to use
X is a vector, so
So we should use a transpose for it.
okay, where? Where exactly?
We can say we can gather all xj's in one matrix.
Yeah.
And then we can use xj minus mu transpose and x minus mu.
Okay, so you're saying that I can put all of the xj's in one matrix, so x1, xn, that's my matrix now, and then I subtract mu from each one of them. Okay, so let me do that. So I have that minus mu, and then xn minus mu. Okay, and then
Multiply that with its transpose.
multiply that times its transpose. Like that. And then
Divide it over 1 over n.
divided over 1 over n. Okay. Okay, I've got two definitions from two different students. Yes?
Shouldn't it be the estimation of mu and not mu? Because technically we won't have mu.
Okay, so I've got, do you object to my making that change?
Sorry.
Okay, good. So I put here the estimator of mu. Okay. Anyone else has any other correction to this? No? Okay, so how many of you vote?
Over n.
Say it again.
Over n.
What should be over n?
Not over n squared.
In here. Okay. In here? Okay. Good. Any other propositions as to what it should be? No? Okay, how many vote for the first option? How many vote for the second option? How many did not vote? Okay, so the second option is correct. And we are going to denote that as sigma n hat. But there is another way to write it, which is maybe closer to that over there, which is the sum of xj minus mu times xj minus mu hat. Okay? So I'm going to put these in here. These are the same thing. Okay? So if you look at the second formula, sorry, obviously I'm missing the transpose there. If you look at the second formula, The second formula is kind of related to the formula you should know. Again, here we should have had that. And obviously, when this is no longer a vector, then you get the square. Okay, but if it is vectors, it needs to be x times x transpose so that you can get a matrix. All right? Okay, so far so good. So let's see. Again, I repeat, I'm given the data. So now I know the x's. First, I can compute the mean, because it's just a quantity that depends on the data. Once I have an estimate for the mean, I can plug it in here, and I can compute this estimate for the covariance. And now everything I've computed, it depends only on the data. So these two quantities are now completely data dependent. Okay. So now I can just pretend and apply everything I did and define now the principal components of the data set now, x1, xn, as, and I'm going to use exactly the same thing as yi equals to ui transpose x plus k sub I. And as before, I'm going to say that u sub I is equal to the I eigenvector. But now it's going to be the eigenvector of sigma n. And then the a sub I is going to be just as before, u sub I transpose, times mu. Okay, there we go. Okay? So now this is something I can compute, because effectively you give me the data, I compute the mean, I compute the covariance, then I compute the eigenvectors, and then I'm done. Okay, is that clear? Again, this is I equals 1 to d, and this could be potentially much smaller than capital D. Okay, so now I have an algorithm. Now this you can implement in a computer. Okay. Agreed? So now I'm going to give you images to do this. Okay? So what is the D in that particular case, if every data point is an image? Well, whatever the dimension of the images are. So it could be millions of pixels, right? So now you're going to have a matrix that is 1,000,000 by 1,000,000. And you have to compute the eigenvectors of a matrix that is 1,000,000 by 1,000,000. And you're going to go ahead and try to do it, and what's going to happen? You're going to run out of memory, even to store that matrix. In particular, what could happen is that the number of examples maybe is not too many. In fact, this is very common in medicine, right? I give you an MRI scan, but I have only 100 patients. And now I have a matrix that is 1,000,000 by 100. But if I compute the covariance needs to be 1,000,000 by 1,000,000. So you will start thinking, well, should I really do the calculation of eigenvectors of a matrix that is 1,000,000 by 1,000,000? Or shouldn't I just figure out a way to do it from the data itself, which is only 1,000,000 by 100? Okay. So that's exactly where we need to do something, because this matrix, as I said, is d by d. Okay? But this matrix, which is just the data, okay? So sigma x and is like this, but the data matrix x1, xn is just d by n. So if d is much, much bigger than n, we are in trouble. Computing the eigenvectors is not cheap. So what do we do? And so that is where this notion of singular value decomposition comes in. Okay, that's the SV. So, any matrix X, that is V by N, can be factorized as X is equal to U sigma V transpose. Okay? Where U is D by D and is orthogonal. So all of the columns are perpendicular to each other. And all of the columns have unit norm. So it's a rotation matrix, effectively. V is the same thing, N by N, and it's also orthogonal. Okay? And sigma is diagonal. Sigma 1, sigma 2, sigma r. Well, it cannot quite be diagonal because it's not squared. So this sigma is D by N. So the idea is that there are R entries that are non-zero, and everything else is zero in that matrix. And what is R? Well, R is the rank of the matrix. And what else? What else? The sigmas are in decreasing order. So sigma 1 is bigger than or equal to sigma 2, bigger than or equal to sigma r, and sigma r is strictly bigger than 0. So all of this, so these guys are called singular values. Okay. Right? So I repeat, any matrix that you have can always be factorized as the product of these three things. One rotation times something that is almost diagonal times another rotation. And what's in the diagonal, it's always real valued, unlike the eigenvalues that can be real or complex. And they're always strictly positive, and they can be written in this decreasing order. Moreover, the number of non-zero singular values is equal to the rank of the matrix. Okay, that's what I've written there. Okay, so far so good. But, well, let me try to do the following. Suppose now that I consider the matrix X transpose X. Okay? And suppose that I have an eigenvalue, eigenvector of this matrix. Okay? Good? So far so good. Maybe I should use a different letter. So let me put a different letter. Maybe I'm going to use Z in here. Okay, so far so good. Then, well, let's use this singular value decomposition for something, right? I know that A is X transpose X, and X transpose is going to be V transpose transpose, so it's going to be V, then sigma transpose, then U transpose, right? That's the X transpose, and then X. So X is U, sigma, and V transpose. So now, because of the property that U transpose U is equal to the identity, then this is the identity. So what I'm going to get here is something like V, sigma transpose sigma, and then V transpose. Okay? Agreed? So now, let me do the following calculation. A times VI. And what is VI? Well, I'm going to assume that the V matrix is just the columns. V1, V2, Vn. Okay? So far so good. So this, by definition, is going to be V sigma transpose sigma V transpose, and then the VI. Agree? Just substituting exactly what I had here, I'll just put it there. Okay, so what is V transpose times V sub I? Well, it's the dot product between every VI here and V sub I. I said to begin with that the V matrix was orthogonal, so all of the columns are orthogonal to each other. So what is going to be V1 times VI? 0. What about V2 times VI? And so on and so forth. So what am I going to get here then? I'm going to get something that is 0 everywhere except in the I, which I will get a 1, and everything else is 0. Okay, so the ith entry is non-zero. Okay. Now, what happens if I go now the next is sigma transpose sigma? Right, what am I going to get if I take the transpose? It's almost a diagonal matrix. What am I going to get? Anyone can tell me? Sigma 1 squared, sigma 2 squared, sigma r squared, right? And then a bunch of zeros. And then the v here. Good? And now, everything is 0 except for the ith, right? So, I'm going to select the ith in here, right? Correct? And then everything else will be 0. So I'm just going to be selecting the ith again. So I hope you are convinced that this is equal to sigma I squared vi at the end of the day. Because from here I only take the ith row, that's going to select the ith column that only has the sigma I squared, and then that's going to multiply only the ith column. Everything else is 0. So I have A times VI is equal to that. Does it look familiar? What is it? Huh? Eigenvector of A. So what I've proven is the following. That VI is an eigenvector of A, but A was X transpose X. And sigma I squared is what? The eigenvalue. So, in conclusion, these U's and sigmas and V's are not completely random or independent, or they didn't fall out of the sky. The V's have a meaning. And the meaning of the V's is that the V's are always the eigenvectors of X transpose X. Okay? Now, you will believe me. I'm not going to redo a bunch of calculations again. But what's going to happen is that the UIs are going to be the eigenvectors of XX transpose. So here I have X transpose X, over there I have XX transpose. Same derivation, you just go through the steps and you repeat everything I did. And well, the sigma I squares are going to be the eigenvector. Well, these are the eigenvalues, so these are the same in fact. By the way, this shows that X transpose X or XX transpose, they have the same eigenvalues. And it also shows that they are positive. So maybe this is sort of an indirect way. I'm not allowing you to use this for the homework though. But this is an indirect way to show that a symmetric matrix has non-negative eigenvalues, because the eigenvalues are these sigma squares. Okay, bottom line. Every matrix X, no matter whether it's rectangular or square, whatever, I can always find a matrix U, a matrix sigma, a matrix V. This is always orthogonal, this is always orthogonal, and this is always diagonal. What are the U's and the V's? The U's are the eigenvectors of X transpose, and the V's are the eigenvectors of X transpose X. By the way, and I didn't say so, these guys have a name. Singular vectors. And these guys here are called right. Singular right. Okay. Cool. So, well, but this seems like a detour. We were talking about PCA, we wanted to analyze data. This seems like a linear algebra class, so why do I care? The reason we went in this direction was because I said we are in trouble. Computation can be too big, the covariance matrix is too big, so I don't know how to compute those eigenvectors in an efficient manner. Okay. Now, what is the covariance? Let's go back, let's go back, let's go back. Aha, here is that covariance. And does it look like something times something transpose? Or does it not? Does it look like something times something transpose, yes or no?
Yes.
Aha, let me go back here. Do I have something times something transpose? Oh yes, I just wrote it. The eigenvectors of something times something transpose are called UIs. And what are the UIs? The UIs are the left singular vectors of X. Okay, so I run out of space, but I'm going to write it maybe here in the corner. So I'm going to write the eigenvectors of X, X transpose are the same thing as the left singular vectors of X. And therefore, if I apply these to covariance matrices, this is kind of saying that, in fact, I should probably write that in words. The eigenvectors of the covariance are the same thing as the singular vectors of the data. Right? Because that's the covariance, that's the data. Okay? So instead of computing eigenvectors of the covariance, and instead of in fact even computing the covariance, which I don't need to, I can just directly compute these singular vectors of the data. And that can potentially be way more efficient than computing the covariance matrix first, which is gigantic, and the eigenvectors of that covariance matrix. So, in conclusion, I'm going to go back here. Now we have this PCA algorithm. Right? I begin with the data. And that is x1, xn. That's what's given to me. Okay? Then, following the algorithm, where did I write the algorithm? It was kind of almost here, right? I need to compute the covariance. I need to compute the covariance, right? Before computing the covariance, I need to compute the mean. So let me do that first. So the first thing I'm going to do is that I'm going to compute the mean. And that is just the average of the data points. Sum of xj's, j equals 1 to n. I need to compute the mean. Okay? That's the first step of the algorithm. The second step would have been to compute the covariance. But I don't want to. I want to do something potentially more efficient. And I've shown you from the far right that the data is enough. But except that, what is the data really? Over there I sort of said x transpose, but look at this formula. It's not quite x transpose. What do I need to do first to the data? I need to subtract the mean. So what I'm going to do is to define this, let me call it x tilde, which is the x1 minus the mean that I just computed, xn minus the mean that I just computed. And so I'm going to call this the centered data. Okay? So I repeat my steps. This is the input to the algorithm. This is the first step, is compute the mean. The second step is to center the data by subtracting the mean from any data point. And now, the third step is I need to compute the singular value decomposition of this centered data. So I'm going to do x tilde equals to u sigma v transpose. Okay? And then I know the result, right? The final result is that I need the eigenvectors of that covariance. But I've proven that the eigenvectors of the covariance are the u's of the SVD. So the principal components that I'm after, right, are going to be, by the way, I probably never substituted, but let me put these two together, right? What is the principal component at the end of the day? Is ui transpose x, and then the a sub I is minus ui transpose mu. That is what it would have been in theory. Immediately you start to see that this is ui transpose x minus mu. Right? Once I substitute. So it's actually almost it's the same idea that I need to take the data, center it, and then project in order to get the principal component. Except that, you know, I already told you this was the ideal principal components if I knew mu and if I knew sigma. But I probably need to work with these ones, right? With this one. So I instead of using mu, I need to use the mu n hat. Mu n hat. Okay, so that is the principal component. Is going to be u sub I times the centering, where u sub I is, well, whatever I already computed. u1, u2, u sub b. Okay? So that's it. So that's why the homework is implement this algorithm in 5 lines of MATLAB code. Okay, so hopefully you know how to do the average in MATLAB without doing a for loop. So that this is really one line. Hopefully you know how to subtract a vector out of a matrix in one line. Hopefully MATLAB is nice enough to you that there is a command line, there is a command to compute the SVD. Okay? And then you're done. Okay. So by the way, in MATLAB you just do SVD of x, and then you just do USV, and that computes the SVD for you. Okay? So that's why it's one line. Is that clear? So that's going to be the second homework, to implement these 5 lines. And I'm not telling you how to do it in one line. I just gave you 1/5 of the homework. Okay, good. Great. So that's what PCA is. It's a statistical definition finding directions of the largest variance. It can be applied to the population covariance. When I don't have it, we can apply it to the data. And in some cases, it's more efficient to do it based on the singular value decomposition. When is that? When the data is big and I don't have too many examples. Typical case in biomedical engineering. When would it be better to do PCA with the eigenvectors of the covariance? In the dual situation, right? If the dimension of the data is small and I have a lot of examples, right? Then the covariance matrix is always dimension of the data by dimension of the data. So in that case, depending on the case, you have to choose. But if you're working with images and big data, it's better to do the SV. Okay. In fact, I'm going to tell you an extra trick here. Let's say I need to compute 2 principal components, or 3, right? After all, we are just a few main dimensions of the data. But the data is images that are millions of pixels. Do I need all singular vectors to do this calculation? No, I just need 1 or 2. So you can tell MATLAB that only computes a few of them. Okay. I forget, maybe there is a parameter that is econ, I think, for the economic SVD, or maybe you can, I forget now, but maybe you can specify that you only want D of them. Okay, we're talking. So think about it, so that makes it even more efficient, because you're telling MATLAB, I just want the first 2 singular vectors, not all of them. Okay, so let me switch gears to the third topic of the lecture, which is geometric PCA. So everything I said so far was sort of statistical. Geometric PCA is a slightly different notion. Though, the magic of it is that it's absolutely equivalent to what I just said. So geometric PCA, the idea is that I've got my data there. Okay? And I motivated this at the beginning of the first lecture. It's just I said, if you take pictures of a face and you change the lighting conditions, the dimension is millions and millions of pixels, but there are only 3 degrees of freedom, which is just the orientation of the light. Right? And I said if I move my head, I only have 1 degree of freedom, just the rotation. So the idea of geometric PCA is simply say, well, if that is the case, then even though the ambient dimension is really big, the data must lie in some sort of subspace of smaller dimension than the ambient dimension. So this is RD, and this is the ambient space, but this is some subspace S, and the idea is that the dimension of S is little d, and this little d is much smaller than the capital D. That's the basics. And so now, given data, the formulation is, can you find a subspace that passes through the data? That's all. And so in a certain way, it becomes a little bit closer to regression, which I think you've already seen, right? So in regression, you have an input data, and you want to predict something else, and you do it through a linear or through an affine function. But that is supervised. Supervised learning means that I know the data, and I know what I want to predict from the data. And I give examples to the machine, and the machine makes the prediction. PCA is unsupervised. So I know there is a subspace, and I'm giving you the data, but there is no labels for classification. There is no Y variables for regression. Okay? So just from the data itself, you want to predict this linear structure on its own. So what that means then is that I need to make the assumption that every data point comes from a subspace. Okay? So how do I write that down? That every data point comes from a subspace. So you might remember that the equation of the line, right? Let me just do the simplest example. You remember that equation of a line from kindergarten. So now, if you put together x and y here, right? This is going to be x, and now mx b. And this is probably something like 1 and m times x plus 0, comma b. Correct? So, a point in the line, which is in 2 dimensions, is always equal to some direction of the line times a point in 1 dimension, because the line is only 1-dimensional, plus some displacement. So more generally, a line is always direction times a variable plus a fixed point. That principle generalizes to higher dimensions as well. If I have a subspace, it has the 2 dimensions. Okay? So now it's going to be something times this vector plus something times that vector plus the fixed vector. Okay? So more generally, for a plane, so this is for a line, for a plane, what I have really is that a point in the plane is equal to alpha 1 u1 plus alpha 2 u2 plus a fixed vector. And we call it mu. So if this is mu, this is the origin, I put mu there, this is u1, this is u2. So any point in the plane, all I'm saying in fact is that any point in the plane can be written as another point in the plane that is fixed plus something in the direction of u1 and something in the direction of u2. That's what it says, a point that is fixed plus something u1 plus something u2. And I emphasize that there are two independent variables here, only because there are two main directions, and that is the dimension of that little tiny subspace. Okay? But I can start writing this in matrix form now by saying, well, this is just u1, u2, alpha 1, alpha 2, and then plus mu. Okay? So that's the equation of a plane. But now we want to do this for big data and more dimensions than 2, so we just do the same thing in general. So in general, the subspace S is going to be the set of points, x's, that are equal to mu plus u1. Well, let me just even write it in a very compact fashion. U times y, where this is a vector in Rd. This is a matrix that is d by little d, and this is a vector now that belongs to R little d. So I'm just repeating myself. If this was a line in R2, all I would be saying that any point in the line is equal to a fixed vector plus one column of u times this. Then when I had a plane, it's a fixed vector. I've got two vectors. So all I'm saying here is the same. Any point in a subspace is equal to a fixed vector plus a matrix that has as many columns as the dimension of the subspace. For the line was 1, for the plane is 2. Here I need little d of them. And then now this vector is the independent variables, which are just little d now. Okay? Is that clear? You've probably seen this somewhere before, in linear algebra maybe. That's just the equation of a subspace. Okay, so with that in mind, what we are going to say is that, okay, so every point j is going to be therefore equal to, can be always be written as such for some choice, but then maybe I'm going to have some noise. Because in reality, you know, the data is never going to be perfectly in the subspace. There is always going to be some deviation from the subspace, right? So that's exactly what I've written here. Every point is going to be equal to some point there, plus that and plus that, and then a little bit of noise outside the subspace. That's the goal. So now I think I can state the problem in the way I want it, which is given the data xj, I want to find the subspace that best fits the data. So I want to find the mu, and I want to find the u that best fit the data. And best fit the data, well, this is the point in the subspace that I don't know. This is the point, noisy point that I do know. So minimizing the error between these two is equivalent to minimizing that amount of noise. So what I'm going to do then is to minimize the error between the jth point and this prediction. And now sum of the errors over all data points. And minimize that with respect to u, mu, u, and y. Okay? And now, even though I motivated it from a completely different perspective, you sort of probably start seeing already what's going to happen, right? What is the mu going to be? The mu, what is this guy going to be? Hmm? Say again?
Mean of X.
The mean of the data. I don't know it yet. I need to prove it. So if the two things are equivalent, then the mu is going to be the mean of the data. What is the u going to be? The u here is, and maybe I'm going to spell it out, u1, u2, u little d, is a matrix, right? But it's going to be exactly what we hope. Here is the basis for the subspace, by the way. But we hope it's going to be the principal directions that I was talking about before. So the basis for the subspace is going to give me the principal directions. And the y's, what are the y's going to be? Those are going to be the principal components as before, these little y's that I've got here. Okay. So in other words, I'm trying to tell you that that's what's going to happen, but I haven't proven it yet. But now what I'm going to prove next is I'm going to prove that the best subspace that fits the data according to this criteria is equivalent to the principal components. So I'm going to prove to you that the mu is the mean of the data. I'm going to prove to you that the u's are the eigenvectors or singular vectors that we had before, and that the y's are exactly these projections that we've got here. Okay. But before I do that, it's always good when you do math to make sure that the way you formulate a problem is well defined, because it could be the case that this thing is not well written in the sense that there could be many extra solutions that I didn't think about before. So, is the solution to this problem unique? Am I going to find a unique mu and a unique basis and a unique everything? What could go wrong? So, a few things can go wrong if you look at the formulation that I just wrote down. So, first of all, notice what can happen. I could be very malicious and say, okay, I'm going to define a yj tilde where I subtract something, or let me actually, do it just like that. Let me just subtract some fixed vector. Invent any y0 that you want, and subtract or add, depending on, from the yj's a constant. What happens? Well, what happens if I do that is the following. I think what I'm trying to say is that instead of u and instead of yj, I can put yj minus y naught, and there is a minus there, and I've got xj, right? And if I now do minus mu, and then minus u times y naught. Okay, that's what I'm trying to say. What about this thing? That's a new mu. Let me call this mu tilde. And that's a new y. Let me call it y tilde. Right? You can see that if you just spell this out, that times that will cancel with this, right? So this is the same thing as xj minus mu minus u yj. So in other words, what I'm telling you is that if you're able to find the mean, mu, well, I cannot distinguish that from the mu times u times y naught for any y naught that I pick. And in other words, if you try to find the principal components, yj, I cannot tell all the yj's from the yj's minus a constant. So in other words, the problem is not well defined as is because I can always shift all of the variables and they're equivalent. I cannot tell them apart. Jeez, this seems terrible. But it actually makes sense because this was my equation for the subspace. Here's my subspace. Then I'm going to pick a point here. And depending on that point that I choose, I'm going to define these two vectors. But why do I pick that point? Why didn't I pick that? Why didn't I pick that? So in fact, any point is equally good. In my definition of the plane, the point in the plane that I pick to define as mu is absolutely arbitrary. So so that's exactly what's going on here. I can translate the plane in a sense, and it's the same plane, right? Because the plane is, the plane is infinity. So if I'm just looking at a small piece, I translate it, but the plane actually, nothing's happening. So the coordinates, I can change them arbitrarily as long as there's a movement inside that plane. So I need to prevent this from happening. I need to put some constraints on either the mu or the u or the y so that this does not happen. Okay? And so to avoid this problem, we assume that the sum of the yj's is equal to 0. In other words, we assume that the principal components are centered. In other words, what we assume really at the end of the day, and you've probably seen these plots of principal components now, for the origin is always in the middle. Once you have a large data set, but you just found a few principal components, they always put the origin in the middle. And that's because it's a convention to remove this ambiguity, to simply say that, okay, the data is going to be centered. So that's exactly what I'm assuming there, that the average of the principal component is 0, and that is precisely to resolve this ambiguity. Okay? So, with that in mind, well, I have to put some other constraint. The basis to the subspace is also arbitrary, right? I can always make a change of basis. So that's another ambiguity that I like to prevent. So one partial way to prevent it is to assume that u transpose u is equal to the identity. So assume that the basis is orthogonal. The columns of u are going to be orthogonal to each other. Okay? We clear now? So let me summarize. We are given data. We assume that it can be well approximated by a subspace. And we want to find the best subspace that fits the data. We're going to do that by minimizing the sum of the squares of the errors, the sum of the squares of the distance from the points to the subspace. But then, to avoid ambiguities, we're going to assume that the y's are centered, and we're going to assume that the basis is orthogonal. With that in mind, now it becomes an optimization problem that I can try to solve. So, minimize this subject to these two constraints. That's the problem. How do we do that? Lagrange multipliers. So I'm going to define a Lagrangian that is the sum of xj minus mu minus uyj j equals 1 prime. What is this business on Lagrange again? What do I need to write down? Objective plus lambda times the constraint. Except that 2 days ago, the constraints were I just had one constraint. And then I had two. But now, okay, I have two, but these are vectors. So let me begin with this one. This is a vector constraint, right? Each yj has dimension little d. Okay? So I have little d constraints here. So if I have little d constraints, how many Lagrange multipliers I need? Little d. And what am I going to do? Lambda 1, first constraint. Lambda 2, second constraint. And I keep adding. Well, that's just a dot product, right? It's a dot product between the constraint, vector constraint. So this is just the dot product dot product between gamma and the sum of the yj's. That bracket notation is the dot product between the first guy and the second. So this gamma is of dimension little d. Okay? Okay, if you did not get it, let me write it once. If I write gamma 1, constraint 1, plus gamma 2, constraint 2, that is equivalent to writing gamma transpose G, and that's the same thing as gamma G. It's just a matter of notation. What I should have been doing is lambda 1, G1, lambda 2, G2, lambda 3, G3. That's the same thing as the dot product between gamma and G, and that's the same as the dot product. This is just a different notation. That's all I've written. Good. So I'm done with this. But now, I have that thing. And now I'm scared to death. This is now a matrix of constraints. So what am I going to do with this matrix of constraints? So if I go to kindergarten, I'm going to write every entry, and for every entry, I'm going to write another constraint, and I'm going to have a long list of Lagrange multipliers. And I've become very lazy. I don't want to do that. So what is the simplest and most compact way to do Lagrange multipliers with matrices? Anyone knows? No one knows? No one knows? Okay, so that's exactly what I'm writing things like this. This principle is identically the same. It's always the dot product between Lagrange multipliers and constraints. So if this is a scalar, it's just the product of the two. If this is a vector, it's the dot product. But if this is a matrix, it's the same thing. Except that now I have a matrix, dot product with a matrix. So I'm going to write it down, plus lambda, and I need to write the constraint, which is the identity minus u transpose u. Except that you said, yeah, sure. What is the dot product between two matrices? Okay? So the dot product between two matrices, A and B, is just the sum of Aij, Bij. So it's really like make them, vectorize them, and then take the dot product. Okay. Fine, good. Okay, are we clear now? We have minimize the sum of the square distance to the subspace plus Lagrange multiplier times this, another Lagrange multipliers times that. Good. So I need to now do the next step. Take the derivatives, set them to 0. So derivative of L with respect to mu. Can anyone tell me what is the derivative of everything with respect to mu? Well, the last term doesn't depend on mu. The second term doesn't depend on mu. It's only the first. So, what is it? Well, I have a sum, so I'll keep the sum as is. Then I have a squared. So the derivative of a squared is 2 times what's inside. So I'm going to put a 2. And then I have xj minus mu minus u times yj. Good? But then the mu happens to have a minus sign. So I need to put a minus here as well. And this has to be 0. So from here, what do I get? J plus 1 to n. What do I get? I get that n times mu is equal to the sum of xj minus mu times yj. Right? You get that? So I'm going to forget about the 2. I'm going to move the mu to the other side, and I just get xj minus that. So that's what I've written here. And that's going to be equal to the sum of the mu's, but the mu's is a constant, so it's n times that mu. Okay. Now this thing is the same as the sum of the xj's minus u times the sum of the yj's. Right? Okay? Sum of the yj's, do we know what that is? 0. So this is 0. And look what happened. Mu is equal to 1 over n sum of the xj's. So the mu is the average of the data points, which is what I had claimed to begin with. And now you start to appreciate why I came up with this centering and saying that the sum of the y's needed to be 0. It's really just a mathematical convenience so that the principal components are centered, and they're centered because I'm going to subtract the mean from the data. So it's almost like a redundant argument there. Okay? So now I've proven to you that the optimal subspace, the mu is just the average of the data. So I need to prove now. So of all the variables, I solve for this. I still need to solve for u, and I still need to solve for y. So let me do y now. Derivative with respect to y. Derivative with respect to y. Okay, so the same business as before. Sum, and I've got 2 times, and I've got xj minus mu minus u times yj. So 2 times the derivative of the square is 2 times the thing. Right? But by the chain rule, now I need to compute the derivative of these with respect to y. And what is the derivative of these with respect to y? Minus u. Okay, the minus is easy. I'm going to put it here. What do I do with the u? Do I put it here? Like that? Does it work? Well, this is d by 1, this is d by 1, this is d by little d times little d by 1. So this is kind of a d-dimensional vector, and I'm multiplying it on the right by a matrix. It's probably not working. So u on the right is not working. Do I then put the u on the left? Maybe I put it here. Does it work? Does it work or not? Rules of multiplication. The dimensions need to be consistent. So what am I missing?
A transpose.
A transpose. So if I put a transpose, then it works. Okay? So rules for derivatives with vectors and matrices are like what you think, but you start to, because matrix multiplication is not commutative, you cannot just put them on the left or on the right and in any random order. You always need to figure out where to put them, and often you need to transpose. Okay? So that's the correct calculation for the derivative. And now we are safe, because after I transpose, this is little d by capital D. That's the u transpose. And this vector is little d by 1. So now all of the dimensions match and everything seems good. And that needs to be equal to 0. Okay? So now, let's see. What I get from here is that the sum of xj minus mu, which is this part, the u is fixed relative to the sum, so I can put it outside. So u transpose. U transpose times the sum, which is these first two terms, is equal to u transpose u times yj. I guess there is some sum as well, right? Right? U transpose u and yj, and that's what we're doing. Now, what is u transpose u? 1?
Or I.
The identity. There it is. So this is the same thing as the sum of the yj's. Right? And what is the sum of the yj's? 0. So from here, something went wrong. Why do we do what? I made a mistake. What's wrong?
Didn't you want to include the derivative with respect to y with the dot product?
Okay, good. That's my first mistake. Indeed. Plus gamma, I guess. But there is a second mistake.
As you get it out.
Huh?
As you get it out of sigma.
How did I?
Get it out.
I don't need the sigma?
I think you cannot get it out of the sigma.
No. Let's go back. I need to compute the derivative of this with respect to yj, right? The first term of the sum depends on y1. The second term depends on y2. The third term on y3, and so forth. So let's say I'm computing the derivative with respect to y1. What happens with the second, third, and fourth, and fifth term? 0. So they don't matter. So I don't need the sum. That's the first thing. So the sum should have never been there. It's just that. And now we're fine. Because again, here's the same deal. I've got this sum. One of the terms matters, and that's multiplied by gamma. So now we're cool. So I can correct all of the mistakes that I had done. So now we're fine. Okay.
Right, sorry.
Now I can sum. Now I'm going to sum. Well, in fact, I shouldn't have erased everything I just erased. Yes?
So the derivative should be derivative of L with respect to yj, not
Yes,
y.
with respect to yj. So now I'm going to sum, and I already showed, didn't I just show that everything was 0? Do you leave me? I just proved that everything was 0 if I sum. So from, I sum everything plus gamma is equal to 0, and I prove that all of this was 0. So bottom line, what I prove is that gamma is 0. Okay. Everything I had before was with a sum, and eventually I got 0, and it was like something is wrong. So I was missing the gamma, and the gamma is 0. Actually, I probably have an n in there before I sum. Okay, so I know that gamma is 0 right now, so I can go back to that equation. Okay? And what do I obtain from that equation? I obtain that yj is equal to u transpose xj minus mu. Right? That's what I obtain. Did I get it right? Did I get it right? Did I get it right? It's exactly here, right? It's going to be the u transpose x minus mu. Except that here it was for one principal component, but I got it there for all of them. Okay? So this is simply saying, in fact, that you take the data, you subtract the mean, and you project, and that gives you the principal component. Okay? So I've proven that the mu is the average of the data. I've proven that the principal components are obtained by taking the data, subtract the mean, and project. The rest of the proof is much more difficult, and I usually take 2 lectures to do it, so the rest of the proof I'm not going to do. So I'm going to say simply that U is the left singular vectors of x1 minus mu. Okay. So maybe just write here theorem. If you keep going and you take derivative with respect to u, and you do a lot of work and use some theorems, then you're going to get to what I was trying to do. Okay? So, in summary, all I wanted to say is that the problem of given data that is big dimensional, extracting a few relevant features is very important. That the simplest approach to doing that is principal component analysis. There are 2 ways of defining it. Definition 1 is directions that have large variance. Definition 2 is find the subspace that best fits the data. And as it turns out, both are equivalent. And the algorithm for finding these components is super trivial. First, you compute the average of the data points. Second, you center the data. Third, you compute the singular value of the composition of the center data. And once you've done that, the principal components are obtained by taking the center data and projecting it onto the subspace. And that's the gist of it. Okay, I think I ran out of time. Okay, so if you have questions or anything about the homework, I guess Ehsan and I can be of help. Thank you.